Hello and welcome. It's wonderful to have you here as we set out to explore the exciting world of artificial intelligence and reinforcement learning. Today, we're delving into a fascinating piece of research titled OpenMOSS Scaling of Search and Learning, a roadmap to reproduce O1 from a reinforcement learning perspective, brought to us by researchers from Fudan University and the Shanghai AI Laboratory. Now, I know that title might sound a bit daunting, but fear not. We're going to break it down and explore the key ideas in a way that's both engaging and easy to understand. Let's begin by talking about O1. In the realm of artificial intelligence, O1 represents a significant milestone. It's a large language model. Think of it as a sophisticated computer program that can generate human-like text and perform complex reasoning tasks. O1 has achieved expert-level performance on challenging problems that require strong reasoning abilities, such as advanced mathematics and programming. But what makes O1 truly remarkable is how it surpasses previous language models by adopting new techniques, particularly reinforcement learning. Reinforcement learning is a type of machine learning where an agent, our AI model, learns by interacting with an environment, receiving feedback in the form of rewards or penalties. It's akin to how we humans learn from trial and error. In the paper we're discussing, the authors analyze a roadmap toward achieving O1 level capabilities from the standpoint of reinforcement learning. They focus on four key components: policy initialization, reward design, search, and learning. Now, let's unpack these terms one by one. First, policy initialization. In reinforcement learning, a policy is essentially a strategy or a set of rules that the agent follows to decide its actions. For large language models like O1, initializing this policy effectively is crucial because these models have vast action spaces. They can generate an enormous variety of possible outputs. Policy initialization involves setting up the model to behave in human-like ways, such as being able to break down complex problems into smaller parts, checking its own work, and correcting mistakes. Next up is reward design. Rewards are the signals that guide the agent toward desired behavior. Imagine training a dog. You give it a treat when it performs a trick correctly. Similarly, in AI, we need to design reward signals that effectively guide the model to produce the right kind of outputs. This can be challenging because, in many cases, the rewards can be sparse or not immediately obvious. The authors discuss different ways to provide these signals, such as shaping the rewards to make them more informative or using reward models learned from data. Then we have search. In this context, search refers to the process of exploring different possible solutions to a problem. It's about the model generating various candidate answers and evaluating them to find the best one. This is important both during training, when the model is learning, and during testing, when it's actually being used to solve problems. The idea is that with more computational resources, the model can search more extensively and potentially find better solutions. Finally, learning. This is where the model updates its policy based on the data generated during the search process. Through learning, the model improves over time, becoming more proficient at solving problems. In reinforcement learning, this often involves methods like policy gradients, which adjust the policy in the direction that increases expected rewards. The authors argue that these four components, policy initialization, reward design, search, and learning, are essential to building large language models with strong reasoning abilities like O1. An interesting point they make is about scaling computation not just during training, but also during inference. That is, when the model is being used. Traditionally, AI models are trained extensively, and then at inference time, they produce outputs relatively quickly. However, the authors suggest that increasing computational effort during inference, letting the model think more, can lead to better results. This echoes human behavior. Sometimes, taking more time to ponder a problem leads to a better solution. But of course, there are challenges. For instance, too much searching during inference can lead to what's called distribution shift, where the model's behavior changes in unintended ways because it's operating in a different setting than it was trained on. The paper also discusses the role of human-like reasoning behaviors in these models. These include abilities like analyzing problems to reduce ambiguity, breaking down complex tasks into manageable subtasks, and self-evaluating and correcting one's own work. By incorporating these behaviors, models can explore solution spaces more effectively and solve problems more efficiently. Another key element is reward design, which we touched on earlier. Designing effective reward signals is crucial because it guides both the search and learning processes. The authors discuss methods like reward shaping, which involves modifying the reward signals to make them more informative, and using reward models that are learned from data, such as human preferences or expert demonstrations. When it comes to search strategies, the paper mentions techniques like tree search and sequential revisions. Tree search involves exploring multiple candidate solutions simultaneously, allowing the model to cover a broader range of possibilities. Sequential revisions involve the model iteratively refining a single solution, much like how a writer might revise a draft multiple times to improve it. The authors also speculate about how O1 might be leveraging these techniques. They suggest that during training, O1 likely uses sophisticated search strategies guided by both internal and external signals to generate high-quality training data. During inference, O1 might be using internal guidance, such as self-evaluation, to refine its outputs. Learning methods are also critical. The paper discusses how reinforcement learning algorithms like proximal policy optimization, PPO, can be used to update the model's policy based on the rewards it receives. They also mention behavior cloning, where the model learns from examples of correct behavior, much like an apprentice learning from a master. It's fascinating to see how these complex components come together to enable models like O1 to achieve such impressive reasoning capabilities. The interplay between policy initialization, reward design, search, and learning creates a powerful framework for building AI systems that can tackle challenging tasks. As we look to the future, there are still many challenges to overcome. Designing reward signals that generalize across different domains, managing the computational demands of extensive search, and ensuring that models learn effectively without undesirable side effects are all areas that require further research. In conclusion, the paper offers a comprehensive roadmap for reproducing O1's capabilities using reinforcement learning. By focusing on policy initialization, reward design, search, and learning, we can better understand how to build AI models that not only perform well, but also exhibit human-like reasoning behaviors. It's an exciting time in the field of artificial intelligence, and I'm eager to see how these ideas develop and what innovations they'll lead to next. Thank you for joining me on this exploration of the cutting-edge research in AI and reinforcement learning. I hope this discussion has shed light on these complex topics and inspired curiosity about the future of AI. Until next time, take care and keep pondering the possibilities.